Okay, the Hungarian algorithm for allocation problems, Supermax edition. I can't believe I said 6 minus 3 is 4. Oh. So, as I'm sure you will watch my previous video about bipartite graphs, this is used for allocating jobs. The difference is that you're using the Hungarian algorithm to calculate the minimum total for allocating those tasks. So now we're talking about actually putting weights on those tasks. You might still want to use a bipartite graph, but you don't have to. I'll show you both ways. What we need to know is what are the steps for the Hungarian algorithm, and I've got them written here. So we've got row reduction, column reduction, and what I like to call the full Hungarian. And after each step, you need to check the allocation. You can definitely allocate after the third step, and checking involves drawing lots of lines. This is going to get messy and involve a lot of different colors. So just pay attention the first time and then play along later. Okay, we're going to take 10, I think I'm up to now. Try and get my arithmetic right. So we have people A, B, C, D, and we're going to give them tasks W, X, Y, Z, and we're going to allocate them so that one of the A, B, C, D gets one of the W, X, Y, Z. It doesn't matter which way around you do it, jobs to people, people to jobs, it's the same result. So to do that, we need to follow these steps. And our first step is called row reduction. And that's because we're going to look at each row by row. So we're looking at the first row, and our lowest number is 3. So what we're going to do is we're going to subtract 3 from every single one of those numbers. So 3 minus 3, 0. 4 minus 3, 1. 5 minus 3, 2. 6 minus 3, 3. Then we look at the next row, which coincidentally lowest number is 3, so we do the same thing, subtract 3 from everything in that row. 7 minus 3, 4, 3 minus 3, 0, 4 minus 3, 1, 7 minus 3, 4. All right, and then we check the next row, do the same thing. What's our lowest number? 3, that's what we're going to reduce everything by. So 6 minus 3, 3. 5 minus 3, 2, 6 minus 3 is 3, and 3 minus 3, 0. Final row, let's check here. Lowest number is 2 this time, so we're going to subtract 2 from everything. So 2 minus 2, 0. 8 minus 2, 6. 5 minus 2, 3. 7 minus 2, 5. Now, we've done our row reduction. We need to check allocation, and we do that by looking for the minimum number of lines to cover all the zeros equals the number of tasks. So we have got 4 tasks. So we want 4 lines just to cover all the zeros. So I'm going to grab my highlighter here. I'm going to do it in purple. So if I look here, I've got 2 zeros in the W column. And it doesn't matter if you do column or row, it's fine. So I've covered that column and wiped out 2 zeros with that one line. Then I'm going to do a horizontal one, and that's wiped out the other 0, and then do another horizontal one, and I've got 3 lines, but I've covered all the zeros. And that means that I can't allocate just yet. I've got to go to the next step. So let's delete that, and then we're going to go to some green, I think would be nice. And so the next step we're going to do is actually called column reduction. So basically we look at each of the columns. There's a 0 in that column, so we don't do anything to that. We leave that alone. If we look at the next column, there's a 0 in that, so we leave that alone. And if we look at the next column, there is no 0 in that column, so that's when we do column reduction. So the lowest number in that column is the 1, so we're going to subtract 1. So 2 minus 1, 1, 1 minus 1, 0, 3 minus 1, 2, and 3 minus 1, 2. Okay, then we look at the next column, and there's a 0 in it, so we don't do anything. All right, then we go through that whole process of the checking again. So we've got to check the allocation. I'm going to grab my purple again. I can do one line like I did last time. I'm going to do another line. It's wiping out 2 zeros. We're looking at the numbers that aren't crossed out. And I do another line, and still I'm covering all the zeros with 3 lines. So the minimum number of lines is 3, but we have 4 tasks, so we cannot allocate. All right, I'll delete all that. So next thing we got to do is what I call the next step. All right, let's delete that. We've done all that. Let's do what I call the full Hungarian. Now, the full Hungarian, this definitely works, so you don't have to check anything else out further. Now, I'm going to use my yellow here because it makes things easier to see. So we're going to put, there's my line, there's another line here, and another line here. So some of the numbers are covered up once, some of them are covered twice, and some of them are not covered at all. So I'll do these numbers in purple. So of the uncovered numbers, we've got a 1, 1, 3, 6, 2, and 5. Our lowest number is 1, so we can cross out 1 and make 0. 1 can make 0. 3 is 2, so we're just subtracting 1 from these. 6 becomes 5. 2 becomes 1. 5 becomes 4. We don't do anything to the covered ones except for the ones that are double crossed. So you can see we've got the BW is double crossed. It's got a column and a row. So we're going to add 1 to that. So that actually goes up to 5. And the 3, which is also double crossed, goes to 4. Okay. Now, using all the numbers we've got there, we should be able to allocate. I'm just going to delete the lines here. And sometimes they just give you in a question the whole thing just like that. So if I was to allocate, remember, we're going to do a bipartite graph. So we've got A, B, C, D, and we've got W, X, Y, Z. And I'll just do some nice dots for this one. I don't always have to do the dots. All right, I'm going to do a lot of colors here. So if I look at this first row, A can connect to W, X, and Y because they're all zeros. So A can go to W, X, and Y because they're all zeros. Let's check the next one when we're building our graph. I'm going to do this in a different color. Let's do blue. So if we check this row, then B can't go to W because it's 5, but it can go to X because we've got a 0, and it can go to Y because there's a 0, but it can't go to Z because there's no 0. So now we're looking at this row and what can C connect to. I'll do that in orange. What the heck? So orange, there is only one 0. C can only connect to Z. If I'm getting this all right. I know someone is out there checking me. Now, if I look at D, again, I've only got a 1, 0, and that's D to W. And I'll do that one in green. So, oop, that's wrong. Missed. D can go to W. All right. Now, if you look at this, you can quite clearly see that there's only one line from C to Z. So C must get Z. And there's only one line from D to W, so D must get W. It's got no other choices about it. Now this leaves us with a couple of options. We could do, well, we got left, what we got left? We got left X and Z for the letters, and we've also got left A and B. So maybe if we look, A will give to X and we'll give B goes to Y. Now, looking at the black numbers under all our scribble, we can see that C to Z is 3. All right. If we go D to W, we can see we had a 2 there. If we go A to X, we've got a 4. Oop, wrong thing. And if we then go B to Y, we got a 4 again. And if you add all that up, you get 13. All right, that was one possible allocation. So we can say that the minimum value for this whole thing is 13. All that work just to get the number 13. Fun times. All right, but you might have said, hang on a minute, what if we give A to Y and b to x, because that was also a possibility from our bipartite graph. So let's swap them around. So if we said a took y and b took x, then obviously these two values change. But if we go and look at this, if we give a to y, that's 5, right? And if we gave b to x, that's 3, that still adds up to 13. So when you've got those two choices, and it's quite common to be given those kind of two choice situations, it's fine to do either. You'll get the same value. And hopefully everything's okay. Okay, here's a Hungarian question example. And they're given us table 1 and table 2. Now, this is a classic way of doing Hungarians on exams, is they actually do a chunk of the Hungarian for you, especially if it's a multiple choice. As you saw with the previous part, it does take a fair bit of time to do this. They just want to check some other stuff, so they're just trying to skip you ahead a bit by giving you table 1, which is the original values, and table 2, where they've done all the row reduction, column reduction, full Hungarian. It says here we've applied the Hungarian algorithm from table 1 to give us table 2. So that's the final result of all her steps. So nothing more needs to be done. So it already tells us that we can do that thing with covering the zeros. So if we cover the zeros, you go 1, 2, 3, 4. It has to be 4. There are 4 tasks, so we know we can allocate. Right. Part A. This is the basic question. In table 2, there's a 0 in the column for Colin. When all values in the table are considered, what conclusion about the minimum total playing time can be made from this 0? Well, that basically it means that Colin gets tour 2. Or it's possible that Colin can do tour 2. That's very straightforward. Now, if you weren't sure what happened with part A, first of all, don't give too much information. But actually, part B is what you need to do to find out the answer for part A. So it's a bit annoying, isn't it? But you can tell with a Hungarian, you're going to have to do some sort of allocation thing. I'm going to do this via a bipartite graph, but you don't have to. And you might find that you can sort of quickly allocate when you're more efficient with your exam technique later. But you're learning, so let's just take it slowly. Our first part is that tour 1 only has 1 for buy. So tour 1 must go to buy, and that's pretty good to know straight off. If we look at tour 2, we got that 0 for Colin and a 0 for Diane. I'm going to do that in a different color. So 2 can go to Colin and 2 can go for Diane. If the common mistake was that people said Colin was quickest, but you can actually see Diane was quickest. So if you, classic case, you can actually talk yourself out of a mark by saying too much. If we look at tour 3, it goes to A and D. So tour 3 goes to A and D. You can see how this is a good color pen exercise. Tour 4 goes to A and B. So let's do tour 4 going onto in blue, A and B. So there's your allocations, but you can already know that obviously 1 goes to B. We've got no choice about that. If 1 goes to B, then 4 can't go to B, so 4 must go to A. And if 4 goes to A, then 3 must go to D. And that only leaves T2 going to C, which was that whole part A thing about Colin. Then let's have a look at our values. Remember, you've got to go back to table 1. This is the table you need to be going back to get those values. So if we look at 1 to B, that's 1 to B. 4 to A, that's 4 to A. 3 to D, that's that one, and then 2 to C is that one. So you can see each person has got their own separate thing. Oops. And if we put the values in there, because actually what it says is the minimum, that's Hungarian algorithm for all 4 tours, which means we have to add them all up. 1 to B was 7, 4 to A is 10, and 3 to D is 18, a bit slow Diane, and Colin gets 8. So if you add all those up, you should get 43. I think that does work. And so the answer was 43, but it does have a unit. If you read the question carefully, it does say in minutes, so don't forget to write the word 43 minutes. Now, this whole table over here, this bipartite graph, sorry, not table, bipartite graph here, you don't actually have to do it. If you can go straight to this without doing the bipartite table, you can just read it from here, then you're okay. All right. Now, as you can see, this is question 8 on the multiple choice, which means it's the last one on the multiple choice section. So it's going to be a bit tricky, but these are the ones you should definitely learn how to do, because if you get them right, then someone else is definitely getting them wrong, and that's when you start to get marks that other people didn't, and therefore you're going to get a better mark and a better ATAR. So these are the ones you should definitely attack and learn how to do. Now we know it's an allocation problem, because we're talking about allocating, and we want to do minimization with allocation. Of course, look, it's Hungarian, we know it's Hungarian, but it does say that there are 2 allocations possible. We've done that before, nothing to be afraid of here, but they're saying basically for one of those allocations, there'll be a child who finishes first, has a lowest value in terms of minutes, and for the other allocation, it'll be another student. And that's what we just want to do. So this is going to take a bit of time. Let's go for it with some Hungarian. So our first step, as always, is row reduction. And so our first row, job 1, it's the lowest value is 5. So this becomes 0, 3, 0, 3, and 2. The lowest value for job 2 is 4. So that's 1, 3, 2, 3, 0. And then lowest value is 5, so it's 4, 0, 2, 0, 4. Lowest value is 5, so 2, 2, 4, 3, 0. Lowest value is 3, so it's 1, 1, 1, 1, 0. Okay. So let's have a look. Can we start allocating, which just means we've got to look at the idea of we need 5 lines as the minimum because we've got 5 tasks. All right, so let's try that out. It's going to use the fluorescent yellow. Look, that wipes out 3 zeros. That wipes out 2 more, that wipes out 2 more, 3 lines, all zeros covered, no good. Let's go to our next step, which we know is column reduction. Column reduction, every column has a 0 in it. Done, that wasn't hard. So it looks like we're going to have to go to full Hungarian because nothing changed, so full Hungarian. Let's bring back our lines. So we had 1, 2, 3, that covered all our zeros. And looking at this, we look at the uncovered numbers. Our lowest value is 1, so we take off 1, so it's 0, 2, 1, 2, 1, 1, 3, 2, 0, 0, 0, 0, and 4 becomes 5. We have to add because it's double crossed. 2 becomes 3, so we add 1 because it was double crossed. And we're all done. We don't have to check the lines. We don't have to because we know full Hungarian will work. Now we just have to allocate. Now you could do the full table, but let's look at how we can do this efficiently. If we look carefully at any rows that have only 1 0, and if you look carefully, you'll see that that's actually job 4. So we know 4 must go to E. And so we can cross out that whole column. And if you want, you can cross out the row as well. So 4 must go to E. Are there any other rows now with just 1 0? Well, that's job 2. goes to Alan because there's only 1 0 here. So we can cross out that column now. Now looking at this, are there any rows with no 1 0? Well, yes, there is. It's job 1 to Chamath. So job 1 goes to Chamath. Cross that out. And as you can see here, Brianna and Deirdre can be both get allocated job 3 or job 5. Now, technically, in this question, if we give job 5 to Brianna, let me just change that. So if we were to give one allocation, I'm going to highlight that in yellow. So if I give Brianna job 5 and Deirdre job 3, that's the yellow one, you could see that Brianna has got the 4. Now we said before that the 4 goes to E. We got 4 goes to E. There's a 5 hidden underneath there, and 2 went to A. There's a 5 hidden underneath there, and 1 goes to C. There's a 5 under. So everyone's 5 in the yellow allocation except for Brianna. So it's definitely going to be Brianna. She finishes first because she's got only 4. Now, if we try out the other allocation, as we say, let's do that in green. That would be to give Brianna the 5 and Deirdre the 4, and the other 5s haven't changed. They should be all 5s. So the only person who's getting 4 is Deirdre. So it's going to involve Deirdre in the answer. And the only one we've highlighted twice is answer B. Wow, that was quite tricky. So just to remind you that we could have done Brianna to job 3 and is that right? And Deirdre to job 5, or Deirdre to job 3 and Brianna to job 5, and their actual timings would have been, now if at E it was, they're all 5, aren't they? 5, 5, 5, 5, 5, 5, phone numbers for Hollywood movies, as you may know. B was going, if B gets 3, then it's 5, and Deirdre is going to get the 4, or Deirdre got job 3 and she was 5, and this one was 4, and that's why we had that answer. Whew, done. Okay, question 8. It's a doozy, this one. Remember, we're going to work through the logic of this, because if it makes sense to me, then I'll get a mark that no one else gets. So we've got this weird situation with these k values, and there's different k values, and we want to work out what is the least value of k that gives us the minimum total to do the job. Okay, let's have a look at how that actually plays out. So they've actually given us that task 1 went to Dorothy, task 2 went to Annie, task 3 went to Buddy, and task 4 went to Chuck. Now, if we were to trade this in, we got pairs or combinations that we could swap for another combination. So for example, if Annie and Buddy were to swap, at the moment it takes them a total of 6 minutes. But if they swap, you've got k plus 8. So you're saying, what's better, 3 plus 3 or k plus 8? And you can see that the maths doesn't work out great for that. To make the value of k so that this total on the right is better than the total on the left, you'd actually have to get at least -2. So k equals -2, not an option. Let's not do that one. If we look at another possible swap, so instead of Buddy swapping with Annie, Buddy swaps with Chuck. All right, so instead of Buddy doing task 3, Chuck does task 3 and Buddy does task 4. So here you got 3 plus 2. All right, that's one possible combination, equals k plus 9. Well, that's even worse. We get k equals -3. So we'd have to have -3 for that to be a swap that's going to give us the minimum amount of time, right? And let's try out the other possible swap. If we swap, we got 4 and 3, would be swapping with k and 5. So 4 plus 3 equals k plus 5. Well, you can actually get that k equals 2. So if we had a situation where k equals 2, that would not change our allocation. If we had a situation, if we put into that k equals 1, then actually that would be a better allocation. You would actually switch the allocation. So if k equaled 1 here and 5, 1 and 5 would make 6. That would be better than the 3 and 4, but we've given the 3 and 4. So k can't be less than 2, minimum 2. If you've got 2, then you've got the two possible combinations, the yellow and the green allocations, both are the same, doesn't matter. So you boss could give either way. If we go k equals 3, then you got 3 plus 5 is 8. 8 is worse than 7, so the 7 allocation is best. But he said, what is the least value of k for which this allocation is true? It works out to be when k equals 2. Bit of a weird one to work out with the logic. If you try and do full Hungarian or anything on this one, you'll probably end up in a complete and utter mess. The idea is just to think about combinations of tasks and their total, and that's why they say in the actual exam things, do inspection, which is again a classic iron brain combo attack, as I like to say.